Good afternoon, everyone. Directed acyclic graph. So this was the topic that we started last time. Directed acyclic graph, DAG. It is a directed graph with no cycle. Now this is important in this definition. That's because if you look on this abbreviation, so directed acyclic graph, so that means it should not have any in the network. Now what does it mean? I'm going to give you an example here. So for example, on network, this is my x variable. This is going into I also have, for example, a z variable, and x is also going into z. I also have a w variable. My y is going into w, and w is going into z, and this y is going into z as well. Now, if you want to see the cycles, either there are any cycles or not, what we do, let's say we start from here. So with the x is going into y, whereas the y is going into z and w. So from the z, you can see it is not coming back to x here, so it is not the cycle. Now from here, from w to z, we have one path here, but again it is not back to x. So we can say that there is no cycle here. If I take another example, so what I would say, there is no cycle. In this example, I have so this is a DAG, directed acyclic graph. Instead of this one, if I take an example, let's say this is x and this is my y, this is z, and this is the w. X is going into y and y is going into w. And instead of this direction, if I choose this direction, now let's see if we have the cycle here or not. So again, I start from here, x, I go to y, and then from y to w, and then w to z, then I'm coming back to my y. So that is what it has a cycle in it. So it is not a directed acyclic graph because I'm coming back to my y here. So what I can write down here, there is a cycle in this, and that's why it is not a directed acyclic graph. Folks, I need to go to the next slide, please. Now there was another word which I wrote down in our last lecture, which was Markovian condition. Markovian condition. I will go into its definition, but before that, I just need to explain you something. Given the set of x, y, which belongs to your E, or an edge. That's what we were also calling as the arc. From x to y, here x is called a parent of y. Now let me draw the same network, the DAG that we discussed in the previous slide. So x is going into y, and x is going into z, and have a w here. Y is going into z, and y is going into w. This is the DAG that we just draw in the previous slide. Now if you look here, this y has impact from x. So the x is called the parent of y. Similarly, you can z has three parents, x, y, and w. Now in this network, I can say that z has three parents. Coming back to our this statement that x is the parent of y, we can say that y is called a child of x. X is a parent of y, so y is called the child of x. If there is a path from x to w, if there is a path from x to w, and if x is not an immediate parent of W X is called an ancestor of W. This is just like the relationship between the grandchildren and the grandfather, or the grandmother and the. Now, likewise, W is called descendant of X. The same thing if you are the grandchildren of your grandparents. Folks, I need to go to the next slide, please. If we assume A, if A is not a descendant of B, example, and also if A is not a parent of B, A is a non-descendant of B. In simple words, if they are not related either in the descendant or the parent's relationship, they are as the non-descendants. Now, using this one, I will define the Markovian condition. Given the set of all its parents, X is independent of set of all its non-descendants. Given the set of all its parents, X is conditionally independent of set of all its non-descendants. There are a couple of notations that we use. The first is parents of X denoted as PAX. Non-descendant of X is denoted as ND of X. And if you wish to show the conditional independence, that is denoted as IP. And then you write down the variable which is under consideration. Then you write down the non-descendant of that variable, which should be, for example, ND of X. Given that the parents of X, which is P of A of. Now, in the next slide, I will take one example and I will elaborate you all these terms there. Folks, I need to go to next slide, please. Now, let's fill off our network. For example, this is my X, and this is going into Y. This is also going into Z. And I have another variable W. Y is into W, and Z is going into W2. And then we have a variable as well, whose parents is Z. For example, we have a network and we want to learn the Markovian condition in this. Now, a couple of things you need to keep in mind. This network is a DAG. Okay, it's a directed acyclic graph. There is no cycle in the graph here. Now, this W and the V, let's write it here. W and V in this network, these are called as the leaf nodes. Leaf node. Now the X here, X is called as the root node because it does not have any. This is the same as you were doing the basic events and the top events in your fault tree analysis. So X does not have any parent, so this is called as the root node. And in this example, your Y and Z, these are called as intermediate nodes, just like intermediate events in your for tree. Intermediate nodes. I will go one by one with each variable and will explain you what are the parents, descendants, and the non-descendants, and conditional independencies for them. So let's start with the nodes here, and we will see what are the parents here. What are the descendants? What are descendants? And what are the conditional independency? Conditional independency. So let's start with the node X here. Now, as you can see in this network, X is my root node, so it does not have any parent with it. So it's an empty set. This is the symbol you use for the empty set. However, in terms of descendants, X has descendants of Y. It also has the Z, W, and the V. So my descendants of X will be Y, Z, and the V. Because X is a root node, I don't have any non-descendant for this. So this will be my empty set again. And again, because X is the root node, it does not have conditional independencies. So this is not applicable even. Now let's go to the variable Y here. If you look on your diagram, Y has the one parent only here, which is X. Now in terms of descendant of Y, I have the W here, which is the child of Y. So I can write it down in the descendant of Y. This is your W. For the non-descendant, your Y is not linked directly with the Z and V here. So these will be your non-descendant for Y. Now I want to write down conditional independence. If you allow me, I will take you to the previous slide and then I will come back here. This is what we are defining here. I have my variable, then I should have the non-descendant of the variables, given that the parents of that variable. So for the conditional independency of Y, it will be your IP. Now we are concerned with the variable Y here, and there are two non-descendant, which is Z and V here. Because there are two, we just write them in the curly brackets. Oops. Given that parent, which is the parent of y, it is x here. How do we solve this? If you wish to solve this conditional independency, it is converted into the probabilistic terms, which is written as the probability of y given that x, z, and the v. Now, if on the network, this z no effect on your y, and the same is true with the v. V does not have any effect on the y, so this conditional probability can be written as probability of y. However, x does effect on your y, it is x will stay there only. That's how you solve the conditional independencies. Now let's go to the another variable, which is z. In terms of z variable, the parents of z is x here. So I can write it down it as x. Now descendant of z, there are two descendants here for z. It is w and the v. And when we talk about the non-descendants here, the y is the only one which is not directly connected to z. So I can say it is y. Now this conditional independence is again, if I want to find out for z variable, this is my z here. And then I write down the non-descendants. So my non-descendants are y. Given that the parent of your, which is x here. Now we are left with the two variables here, w and v. Instead of going on the next slide, if you allow me, I can delete this. So let's say we find out for w now. Now the w has two parents, y and z here. So I will have y and z. Now for w, there is no descendant here. So it will be an empty set. Now for w, the non-descendants, v and the x, because there is no immediate link between them. So this should be my v and x. Now again, when we write down the conditional independency, it should be, we are talking about our w variable, and there are two non-descendants here, v and x. So this is the v and x. Given that the parents, there are two parents for w here and z. This is your y and your z. Now the last variable is v here. For the v, we only, which is z. And again, we don't have any descendant for the v, so it will be an empty set here. However, in terms of non-descendants, we have x, w, and y as the non-descendants for v. So it will be X, W, and Y. And let's write down the conditional independence using this information. So we are talking about the variable V, and we have three non, so it will be X, W, and Y, given that the parents, so the parents of V are Z. This is how we develop conditional independencies. Folks, I need to go to the next slide, please. One thing you need to remember, if your network is a DAG, directed acyclic graph, and it has the Markovian condition, which we just discussed, both of them, only then it is called as the Bayesian network. So your network should be a DAG, it should be directed acyclic graph, and it should fill up the Markovian condition. Only that is we call the network as a Bayesian network. Now, if we want to find out the joint probability of your network, now in our network we had X, Y, Z, W, and V. So the joint probability of your network should be X, Y, Z, W, and the V. Now I will take you to the network in the previous slide. So this is my root node. So the only probability should be P of X. So that should be equals to P of X multiplied by. We're interested to find out the probability of Y. Now if I go back to my work here, the Y has the input from X only. So it will be the X given Y given that X. That's because X is the parent of your Y. Similarly, if I want to find out the probability of Z here, if you look at your network, Z has a parent of X, which is immediate parent. Times the probability of your W. Now for W, it has two parents here, Y and Z. So it will be probability of W given that Y and Z multiplied by the probability of your V. Now if you look at your network, the V has only one parent, which is Z here. So that's how you find out the joint probabilities of your network. Now there is one thing which we call as the Bayesian inference. I will write down the definition and then I will take one example to explain this. A method in which Bayes' theorem is used to update the probability for a hypothesis as more information becomes available. It is a method in which Bayes' theorem is used to update the probability for a hypothesis as more information becomes available. Now, this more information in Bayesian analysis is what we call as the evidence. Now, before I go on the next slide, I just want to mention the example I'm using here. This example or the previous slide is based on the structure of the network. So every Bayesian network will have one solution based on their conditional dependencies or independencies. Folks, I need to go to the next slide, please. Now, this Bayesian inference, I'm going to explain you using an example. For example, let's say we have a network where we have X, the Y. Y is the parent of Z. Z is the parent of W. Now, in this network, your X is the root, and this is your leaf, W, and both of these are your intermediate events. If we know the probability of your X and the conditional probabilities of your intermediate events, we can find the marginal probabilities. How we do that? Let's suppose I assign P of X1 is equals to 0.4. Okay, let's consider all nodes as binary. So by that I mean to say there are two states associated with each node. So it could be a success or it could be a failure. Supposing them as 1 and 2. And as you know that the probabilities of let's say for x1 and the success probability and your failure probabilities should be equals to 1. So if I'm given with the px1 and it is a binary node, so the other probability of 2, that will be is equals to 0.6. Similarly, for example, I'm given the probability for y, I'm giving the probability of now it can have either x1 or it can have the x2, because there are two states of the x as well. If I'm given this value as 0.9 and this value is suppose 0.8, now I can easily calculate the other states here. I can find the probability of y2 given x1, that should be equals to 0.1. Similarly, I can find out the probability of y2 given that x, that is equals to 0.2. Now let's come to this variable z. If I have the probability of z1, given that again there are two states of its parent y, this is y1 and this is my y2. For example, this value is 0.7. So I can find out the pz2 given that y1 as 0.3. And if this is 0.4, I can find out the other state. Now in terms of your leaf node, I have p of w1 given that the parent state 1. For example, this is 0.5 and probability of y1 given that z2 is the 0.6. And what we want to find out the marginal probabilities of intermediate events, which are y and z. That's what we want to find out here. Folks, I need to go to next slide. Now, how we solve that? We use the law of total probability. This is the solution here. Use the law of total probability. Now, if I want to apply the law of total probability on to find out the state 1 of y, now this one should be equals to your p of x1 because I know there are two states associated with x times your p of y1, given that. Now if you allow me to take you to the previous slide, so now you can see that y has the parent of x only, so this will be x1 y1, given that x1 state plus the second state of your x, which is p of x of 2, and that p of y1 x. Now again, all this algorithm will change if your network structure is changed. Now for this one, I know my value is 0.4 multiplied by p of y1, given that x1. This is the value which is given to me, which is 0.9. And plus the second state, it should be 1 minus 0.4, which is 0.6, times, this is the probability of the y1 given that x2. If I take you here, this is the 0.8. So once you solve it, you will get your marginal probability of y1 state as 0.84. Now this is the value of my probability of the y1 state. Now again, if I want to find out y2 here, so that should be equals to 1 minus this value. And this turns out to be 0.16. Let's find out the marginal probability of Z. If I this network here, now Z has the parent of Y. So I will be using two states of Y here, Y1 and Y2. So this will be the probability of Y1, probability of Z1 given the Y1, plus the second state is the probability of y2, is the probability of your z1 given that y. Now this value we just find out 0.84, the marginal probability of y1, so that should be 0.84 times the probability of z1 given that y1. Let's go back to the network and see this value. So this is the value which is 0.7 here. Plus this probability of the y2 is 0.16. That's what we find out here. It should be multiplied by the probability of the z1 given that y2. Oops, sorry. So probability of the z1 given that y2 is 0.4. Now once you solve it, you will get 0.652. Now this is the one state of Z, which is Z1. For the other state of the Z, which is Z2, that should be equal to 1 minus 0.652. It is 0.348. Now, similarly, when you calculate for your W2, let's do it for W1 first. You will get it 0.5. I'm just writing down the answer here, 0.348. And according to this, your value of probability of W2 will be equals to 1 minus 0.5348. I don't have his answer calculated, but you can calculate it. Now, that we just studied, this is called as the message passing algorithm. It is named as the message passing algorithm. That's because every parent has a message for their son or the child. As you can see that we have this information, only then we were able to find out this information. Once we have this information, then we can find out this information. That is why it is called as the message passing algorithm. Folks, I will go on the next slide, please. Now, there is one thing which is called as the instantiation. Instantiation. If node is known to be at one of its states, it is said that node is instantiated. Now, what does it mean simply? If you have, as we are doing X here, for example, and it is a binary, which means it has the state x1 and it has a state of x2, for example. It is a binary. And if we know, let's say x1, that is what we call as the x is instantiated because its state is null. Now, the algorithm that we just performed here, if I take you to the slides back here, as you can see, we are going from X to Y to Z and W. This kind of the propagation is called as the downward propagation. This propagation is called as the downward propagation. In some of the textbook, you will also see it as the forward analysis. Forward analysis. Now you have noticed we have used two things. One is the law of total probability, sorry. We have used the law of total probability. And we have also used the Markovian conditions. That's what defines our BN. Folks, I will stop it here. I will take your questions if you have any. We will work on some more examples in our next lecture on Tuesday. Hadis is asking, can we say that the parent is the input? Yes, you can say that, but the most appropriate word in BN analysis is that X has the impact on Y if X is the parent. In a layman language, yes, you can write it down as a parent is the input, yes. Folks, are there any more questions for me? Okay, it seems like you don't have any more questions. I will upload this lecture and just go through it again. And if you have any questions, you are more than welcome to ask me. And I will see you on Tuesday. Have a good weekend, everyone. Thank you.